this. Now, look at this. What the hell is this? This is class 9 physics. Honestly, I pity the people who are forced to deal with this monstrosity. Its horrors just terrify me. But don't worry. In this video, I'm going to be dealing with every single concept dealing with 9th class physics in just half an hour. Woo! So make sure you have a really strong concentration because everything I'm going to go with is going to be fast. Let's start off with, when you're dealing with physics, you're always supposed to divide it into 3 parts: kinematics, dynamics, and what's left of it. What we're going to deal with now is kinematics, which deals with the behavior of an object as time passes by.
Actually, it's 4 dimensions because Einstein stated in his theory of relativity time is a dimension affected by gravity.
Shut up! Honestly, you don't have to listen to nerds who poke you into learning new things that aren't even relevant to you. All you have to do is be familiar with content that you will be sufficient with when you're dealing with class 9. Back to the point. The universe consists of 3 dimensions: length, breadth, and height. But you only have to deal with the first dimension. Now imagine yourself in a situation where you're entrapped in a cage and the only way you can escape it is through a tunnel which is all the way at the back of the wall. Ideally, you would have to go through the tunnel to make your escape, but you could do it this way too. If you did have a key, you could just open the door and make your way towards the exit in the same manner you did using the tunnel. Before we move into this, let me familiarize you with the values of scalar and vector. Most values don't have a direction in which it is increasing or it may be decreasing. So these values may be considered as scalar quantities. On the other hand, there's values which depend on the direction and the values. These values are what you refer to as vector quantities, and they have a probability of cancelling out each other depending on the direction that 2 different vector quantities are facing in. Now, if you were to analyze this situation, you would observe that there's either the shortest path that you have traveled from the cage to the escape. This is what you refer to as the displacement, the shortest path that you have traveled. This is a vector quantity. On the other hand, if you were to use the tunnel in order to make yourself out of the cage, the total path that you might have traveled from the cage to the escape is going to be the total distance. That is the sum of the distances that you have traveled, regardless of the direction. This is a scalar quantity. Dividing both the values by time respectively, you would receive velocity and speed. Now the values that we have considered here are just regular values. If you were to consider the average velocity, you would have to be taking the difference of the final and the initial displacement and divide by the final and the initial time. Average speed is often the sum of the final and initial speed divided by 2. But make sure you observe the question for the time provided because it could also be the total distance upon the total time. Now, if you were to consider the difference of the final and initial velocities and divide that by the total time, you would be receiving acceleration. This brings us to another part of kinematics, that is mainly just math. I mean, math is equally terrifying as physics because honestly, who the heck is going to deal with all of these calculations? But this is what we have to deal with because physics and math coexist with each other. This is why a prominent figure of physics, Newton, stepped up and brought us 3 equations. These are the equations of motion. These are as follows: V equals to U plus AT, which can be derived from the formula of acceleration, S equals to UT plus half AT square, which can be derived if you were to consider the area between the line graph and the axes. This brings us to graphs, another part of physics, which deals with the interpretation of the motion of an object in the form of lines. To be honest, if you have to deal with graphs, you just have to be a little creative. But you'll also have to observe the values that have been provided to you, regardless if it has to be between velocity and time, position and time, or acceleration and time. S equals to ut plus half at square over here is the sum of the areas of a triangle and the rectangle below the line. V square equals to u square plus 2as, which is another formula that can be derived by multiplying the formulas derived from average speed and acceleration. There's another concept regarding kinematics that deals with the type of motion that takes place in an object. It could be how regular or let's say uniform motion can be. If it meets the criteria as such, then it's a uniform motion. If the motion of the object does not seem to behave regularly, not in a pattern, then we can say it's a non-uniform motion. Ideally, if you were to consider the motion of an object in a circle, you would have to consider it as a uniform motion. This is where you consider speed, the circumference divided by time, as the speed of the motion of an object in a circle. And on the other hand, the displacement would be zero, because as you move from the initial to the final point, both of them intersect at one point. So yeah, the average velocity would be zero in a circle. Dynamics deals with the sources of the motion of an object, that is, force. I mean, honestly, the object won't start levitating by itself for no reason. The most simplest and the boring definition of force is a push or a pull, but that's something you don't have to deal with. This is how you define force. It's the tendency of an object to change the state of motion of another object using some sorts. This can be done with or without the contact with the other object, except telekinesis. That isn't real. If you were to define force mathematically, you would consider the product of the mass of the object and the acceleration it is having. This brings us to the laws of physics, or the laws of motion that Newton came up with, so that we won't lose our minds while deciding whether an object is or isn't following the laws of physics. I mean, if it isn't, then you're free to lose your mind. The first law states that forces can actually cancel out each other, because forces are actually vector quantities. So yeah, they do have the ability to cancel out each other, depending whether if they're having a positive or a negative value. If they do cancel out each other and equate to zero, then the object will stay in the same state of motion that it was before. This is what you define as inertia. Inertia is also responsible for you smacking your face on the floor of the bus when it stops at one point instantly. A second law of motion says that if they were to not cancel out each other and unbalance the forces, this would lead to the sum of all the forces equal to the mass into acceleration of the whole system. And the third law of motion states that nature hates everything and it always opposes them regardless of what forces are being applied. The fourth law, which is in the part of the first three, states that the momentum, which is the product of the mass and velocity of an object, is always conserved in a process of either be it collision or just regular movement. Okay, this is how you can understand it. Imagine me throwing a ball at you and it sends you flying away. Now, let me just analyze this for a second. If you were to consider the masses of the ball and you and multiply both of them respectively with their own velocities and then add them up, you would receive your initial momentum. If you were to do the same for the final situation that takes place as you fly away, you would also have the same value corresponding to the first. This is what I stated before, momentum is conserved. And this is what you refer to as the law of conservation of momentum. There's infinite sorts of forces that may take place depending on the situation you're placed in. But there's only a few main forces that you have to deal with. Normal force, just a regular push or pull. spring force, which is the product of the spring constant depending on the material the spring is made of and the displacement that has taken place in the spring. Frictional force, which is of three sorts: static, kinetic, and rolling. Tension force, which is the force applied by a string, usually in the sorts of pulling. This tension force is always divided equally among the sections of the string. So summing all of them up would provide you the average tension force applied by the string on an object. And buoyant force, which we will be dealing in this video sometime after. These forces that are referred to as are known as contact forces. But there's also forces that don't need contact. I mean, all these forces that you just observed aren't actually contact forces. They're just repulsions or attractions between the atoms of an object. This is what we refer to as electrostatic force. Magnetic force is the repulsion or the attraction between two magnets depending on the poles that face each other. And then we have gravitational force. Now, gravitational force is a unique sort of force because it also deals with the force that takes place when an object is in circular motion. There's mainly two forces that apply on an object when it is in circular motion. These are referred to as centripetal, which is towards the center, and the other, which is centrifugal force, which usually diffracts away from the center. Gravity has a tendency to pull on an object from all 360 directions. Both of these motions cancel out each other in order to provide you a uniform circular motion, as I have stated before. But unless and until you were to cancel out one of the each, the object would travel in a direction it was pointing in, that is the tangential to the point. Gravity, as I also have referred to before, is a centripetal force. It attracts objects towards the center. Gravitational force mathematically can be defined by the product of the gravitational constant, the masses of both the objects in the system, and divide the whole thing by the distance squared. If you were to remove the mass of the other object which is being attracted, here you would receive gravitational acceleration, because we are aware that force is the product of mass and acceleration. The mass that you have removed will only leave you with acceleration. Okay, but why is gravity considered to be an acceleration? If you were to throw a ball towards the earth thousands of kilometers away from it, you would realize that the distance keeps reducing. As the distance decreases between the object that you have thrown and the earth, the gravitation value will increase. This way, the distance will decrease more, and the process repeats itself. This is why you refer gravity as to acceleration.
Now, if you were to multiply the mass into the gravitational acceleration, which is usually 9.8 on Earth, you would receive the value of weight. Now listen really carefully. There may be some differences between weight and gravitational force. I mean, they're both forces, but at the end, the difference being the gravitational force depends on the mass of both the objects, but weight only depends on the mass of the object which is being attracted. So yeah, gravitational forces may be applying on each other simultaneously, but when we're considering weight, you're only considering the object which is having gravitational acceleration, which is pulling another object with some amount of mass. How about dealing with fluids now? You see, everything we've been dealing with now were just normal objects, solids. You see, if you're considering fluids which have a unique system of forces, you would observe that forces are being applied on the body from every single direction. The first law of motion would contradict the peculiar behavior of objects which are being submerged in water. Thus, we came up with the term pressure, which is force being applied per unit area. Mathematically, pressure can also be defined as the product of the density of the liquid, the height from which the object has been submerged, and the gravitational acceleration. But how can we explain the behavior of an object floating or sinking in the fluid? Well, thanks to Archimedes, originated when he found out that the product of the volume being displaced by an object submerged in water into the density of the liquid into the gravitational acceleration will provide you the value of buoyant force. If you were to equate this with the weight of the object, you would find out that the object may either float, sink, or stay submerged. Oh, and yeah, the ratio of the object density upon the density of water gives you the relative density of the object. Now let me ask you a question. When you're studying, sitting at your place, are you really working hard enough? 'Cause you're not! You haven't displaced your body, man. If you were to displace your body with the help of some force being applied on you, you have done work. So you can say that the force being applied on the object multiplied by the displacement that the object has done is equal to work. But yeah, make sure that the force being applied on the object and the displacement that has taken place must always be in the same direction. Unless it's not and it's the other way, that is the opposite directions, then the work done will be negative.
This is because force and displacement are vector quantities, but apparently work is a scalar quantity. When some amount of work is done, that's where you receive energy. Energy cannot be described as anything. It's not an object. It's a mere presence for the capability of an object to carry out some activities or some processes to take place. For example, you're literally an energy machine. Energy runs through you, in and out. You eat some food, you process that into carbohydrates, it turns into glucose, and there you have it. You have energy. Other than that, you use all of that energy up for processing your thoughts or watching this video or anything. In general, you could describe energy as the capability of an action to take place. Energy can be of sorts. There's sound energy, heat energy, light and solar energy, which are a part of radiation energy, electrical energy, nuclear energy, chemical energy, energy that is being produced by the presence of force in an object or over an object, and the energies that we are going to be dealing with, mechanical energy, which consists of kinetic energy and potential energy. But what's common about all of these energies? Everything! In fact, all of these energies are literally the same in the terms of value. You see, all of these energies can have the same value. They can convert into each other and then go back to the same form. All that changes is the form. It's just like you changing your clothes. Nothing much. This law is what you refer to as the conservation of energy, which states that energy can neither be destroyed nor be created. It can only change its form, just like matter. You can consider these energies as state of energies. Now, let's deal with a specific form of energy that I referred to before. Mechanical energy. The only way you can characterize the form of energy an object possesses depends on the state of motion that the object is present in. So let's consider these forms of energy. The first one we are dealing with here is static energy, or what it's famously known as potential energy. Potential energy is of different sorts, but you can define it in general as the form of energy that an object possesses or stores before it is in motion. It will always have a force which is being applied on it, yet it may not be moving. There's two of these sorts. There's elastic potential energy and then there's gravitational potential energy. If you were to take a spring on which the object has been pressed on, but it's still intact because you've kept your hand in that position right there, this is what you refer to as elastic potential energy. The energy has built up into that spring such that it's going to provide some force onto the object and release it with maximum effort. The formula of this sort of energy is half kx squared, the k being the spring constant, which depends on the material itself. On the other hand, we have the gravitational potential energy. An object maybe at some height h may have some weight mg. When you multiply the both of these using the general formula of work, which is F into h, and we are aware that mg is also a sort of force, we can say that the potential energy which an object will be possessing due to the presence of gravity will be m into g into h. Okay, so now let's say I dropped the object from some height, or I threw it with some force from the height I had kept it at before. The object will now enter a state of motion, and with the state of motion it will also have some velocity, regardless if it's constant or not. The object will now possess kinetic energy. Now anything in motion will have some velocity, as I stated before. So the formula of kinetic energy is going to be half mv squared. Now the example of the object falling, when it had some potential energy, I left it into motion. So now you'll have to equate that to half mv squared because of the law of conservation of energy, which I have stated before. And as you equate these, you'll receive the value of velocity, which is root 2gh. As I stated before, work is scalar quantity, and thus energies are also scalar quantities. But since we're aware that the components to calculate work are vector quantities, displacement is a vector quantity. Therefore, we utilize velocity and not speed. And at last, if you were to consider work or energy and divide that by time, you would receive power. Also, the commercial unit of energy is kilowatt hour. This brings us to the last topic of physics, 9th class, sound. Before we understand what sounds are, you have to understand the behavior of the sound. This is where we consider using the theory of waves. Now you can't really define waves either, but the only way you can understand them is a back and forth motion or disturbances in an object. And since sound propagates just like light or any other radiation, it is also considered as an energy. But hold on a minute! What about mechanical energies? Well, you shut up and listen. Now, yes, because you can store sound energy, that's literally why it's propagating through material. It can also be considered as a kinetic energy, no? Because it's literally passing through the object as it moves, like for example, air particles. The point is, be it light or be it heat itself, these are all radiations, these are all waves. But sound is a wave too, right? Then why is it so unique from the other ones? It's because it relies on a medium to travel through. This is why we refer to another categorization of waves or energies in general. If a wave depends on a medium like water or a metal or gas, then it's a mechanical wave. But if a wave does not depend on a medium and is produced through the presence of an electric and magnetic field, which is not relevant to you, then it is referred to as an electromagnetic wave, which is also not relevant to you. Now, how about understanding a wave right here? Alright, look at this wave. It's kind of up and down. Look at this zigzag. It is smooth zigzag. There are some characteristics that the wave has which affects the way it moves or affects what you're listening to. The upper part of this wave is what you refer to as the crest, and the lower part is what you refer to as the trough. If you were to consider the distance from the line that passes through the middle of this wave to the top or like the maximum height of the wave, then that is what you refer to as the amplitude. It's always going to be the same regardless if we're considering the upper part or the lower part. Now, if you were to take a section out of the wave, starting from the upper part of the wave and ending the lower part of the wave, the distance between these is what you refer to as wavelength. Now, if you consider numerous waves to travel in a specific amount of time, that is what you refer to as frequency. Oh yeah, just one thing that I forgot to tell you. The wavelength and the frequencies are always inversely proportional to each other. Now, since I referred the term time, that also means that the wave that is traveling will also have some velocity, and in some specific distance, if these numerous amounts of waves have traveled, that is what you refer to as wave number. Now, this may be a little painful, but this is not the only sort of wave that I just referred to. This is what you refer to as a transversal wave. A wave may not necessarily have to look like a transversal wave. Sound can behave as two sorts of waves. This one is what I refer to as a transversal wave, and the other one is what I refer to as a longitudinal wave. Just like the crest and the trough, the longitudinal wave has its own sets of compressions and expansions. The compression or the contraction is the part of the wave which has a higher density. The rarefaction or the expansion is the part of the wave that has the lowest density. You can understand this as the movement of a caterpillar, Sound can also be reflected away or get absorbed, since it always needs a medium to travel through, regardless of what sort of matter it is. This reflection is what results in echoes. Another property of sound is it always reflects like light in an equal angle. That would mean that if you were to draw a normal which is bisecting the angle of the reflection, and both these angles turn out to be equal, this is what you refer to as the law of reflection, which applies to both light and sound, as I said before.
This is a very significant property of sound which allows animals like bats and dolphins to locate themselves or use it for communication or locate their food using the process of echolocation.
And at last, another final phenomenon of sound. It has this property: if it keeps consistently colliding with a surface, it will gradually lose its consistency as it gets absorbed and will go mute. This is what you refer to as reverberation, and you can usually observe this in an opera, even if you could afford to get into one.
I know you can't afford one, so here's the deal. You walk into a room with something absorbing all of the sounds and scream at the top of your lungs. And you will observe as you scream, your voices fade away. Oh my damn! I barely found time to make this video. So I'd be really grateful if you subscribed or maybe liked the video. Don't mind the sawing machine, just subscribe, alright? Just try not to be hateful in the comments, that's all I need. I'll see you next time in a gaming video. Bye!